So let's get started. Here our agenda again in a written form in case you think I rushed it in the overview video. As I mentioned before, in the second part of this lecture we will have the coding, where we have a neural network to do the handwritten digits classification from the image dataset. This dataset contains an image like the one I'm showing here. This is an example of digit number 3 in a handwritten form. What we are interested in is having a model. I call it here a machine or a model sometimes. We are interested in having a model to identify the image. By identifying, I mean that we feed the input to the neural network as an image like this, and the output should be the corresponding label like a 3. So ultimately, we will have a neural network to do this job for us. But we will start simple. So as many things, I prefer to have like a smaller version of the problem and start with this smaller version of the problem, then gradually develop it. So that's what we are going to have here. We still have the same requirement of the model that I explained before, that we will have the input image as a handwritten digit like an 8, for example. The output or the prediction should be the corresponding label. It's not necessarily a single class. In fact, this is common in many classification problems. You would have many classes, and you are interested in having a correct prediction of all of them. So you could have a 6 or 9 or any other digits. Now let's just stick to those 3 and think of how this model would be. It needs to be intelligent at least. We could have a long debate about what intelligence means, but for the purpose of this lecture, I mean it's capable of recognizing the pattern. And what I mean by this, that if we just take the example here, digit number 8, and we are not interested in this example per se, we are interested in having a model capable of recognizing other examples like this. Not only those, but also other unseen examples. So we don't need to go through all the list of all possible ways to write the digit 8, which is infinitely many ways. We are interested in having some way of recognizing this pattern so the model can generalize to the future unseen digits and still predict them correctly. So the second thing is that the model we should be able to learn the model efficiently. This is intuitive because we might have the best model for doing this job, but we might not be able to build it easily or fine-tune it for another task. And even if you have the best model, if it is not easy to tailor it for a new task or modify it, it might not be useful in practice. So focusing on the first requirement, which is recognizing the pattern. I have a restriction here that I made to simplify the problem, that I constrain myself to those 3 digits, 8, 6, and 9. And say we are interested in building a classifier for those only. One way to think of the way to classify digit number 8 is to have some kind of rules or heuristics that guide us for doing this classification. I will clarify this. But say the way I look at digit number 8, that, well, this is like a concatenation of 2 circles, one on the top and one on the bottom. This is like a generic feature. I mean, it applies not only to the image here, but probably applies to many other images with arbitrary degrees. So this is like a general feature. I call it a whole. So what I'm saying here, that to classify this in a general way, you might say, if the image has in the top part a whole and in the bottom part another whole, then this is probably 8. Applying the same rule to 6, you would have the feature missing. I would call the whole as a feature. You will have this feature missing in the top part but present in the bottom part. For 9, it's the opposite. And the way we extract those features or description, we are not interested in this for now. Let's just assume that it's provided for us. We have a way to extract this feature. Later, we should have the neural network to be able to do this as well. But for the purpose of this example, this is the second assumption I'm making, that we are having a way to get those features for us. So you give the image, it tells you the top part is like a circle or not, and the bottom part is like a circle or not, and you have this in a digital form. So 1 means that this feature exists, and 0 is an indicator of the absence of this feature. You give this to your model, and you should have the correct prediction, like an 8 here, right? So this was just a way for introducing the perceptron. This circle is an indicator of the perceptron concept. We have input, which are features or descriptors, and then we have the prediction. So what are those features? It could be anything, but the example I have showed previously is like 1 or 0 as indicators of the presence or absence of a circle. Let's assume that we still have those features. So you have 2 inputs to your perceptron. Now, how much you expect those features will be present, how much they impact the prediction of the network? We have weights to quantify this effect. By this I mean we could have weights, high weights for the first feature and second feature. In the example here, it says that I rely too much on the presence of the circle on the top part, and also with the same degree I rely on the presence of the circle on the bottom part. So these 2 circles must always be there. I assign high weights to this, otherwise I will not predict the input as 8. But if you look in the real world, you might say, well, an example like this, well, the circle on the top is not very clear. So that's why you say, okay, I need to adjust the weights. I will tolerate some degree of distortion in the first feature by having a lower weight associated to it, okay? So again, you have features, you multiply those features by weights, okay? So what do you do after that? You have to combine all of those, and we do a simple summation for this purpose. And after this, you would have a value based on which you judge whether this is a digit 8 or not. And this is where I call we are doing the prediction of a class or not the class based on weighted evidence. So this is a weighted evidence that comes from the features. We weighted them, and based on the final value, we want to make the prediction, okay? That prediction is a binary prediction because we have two classes, 8 or not 8 in this example. And the way we say that this is the correct class is that we have a specific threshold. So if the weighted evidence is greater than this is threshold, greater than or equal a specific threshold, what happens that the perceptron fires. That's why I have this symbol here. And when the perceptron fires, we expect this as a positive indicator that this is a class we are interested in. So it's like a binary classification problem. It's a very simple way to get to your decision, to get to the target class by saying, I will weight the features that are used as an input to the perceptron, and based on the sum of those weighted features, I will compare against a specific threshold, and if it is greater than this threshold, then I will produce 1 as an indicator of the digit 8 or 0 if it's any other thing. Okay. So, well, the important question here is that how do we calculate those weights? This is what we call learning the model, and we will talk a lot about this in more details in a later part of this lecture, but for now we can just guess it because it's a simple model. For example, if we have 8, we know that the circles or the features that I mentioned will always be present on the top and bottom part. So we will assign a weight value for 1 for each of the 2 features. And of course, when you sum those, you will have a value that's 2. So you can set your threshold to be 2. So anything greater than or equal to 2 will produce 8. As you can imagine, if any of this feature is absent, you will not reach that threshold, and you will have also the correct prediction as not 8. If you want to have the same perceptron for classifying 6, this is what you could have for those weights. Remember, those are not unique values. You could come up with other values. For example, when you change the weights and they also change the threshold, you could have many other possible configurations. So this is not the unique or the only way to do the assignment of the weights for this perceptron. Also, you could have for 9 those weights. You can check those and come up with other configurations for this. All right. So back to the first requirement that I mentioned. Now it seems that we have a good way of classifying or recognizing the input digit, because we relied on some kind of feature that's generic enough and allows us to identify or classify correctly many input images as long as they are belonging to the class we are interested in. The examples here should all have those features that I mentioned on the top and the bottom part of the image, and this classifier should work reliably. So, but this is before moving to the second part about learning the weights. Let's have one more thing to discuss about the capability of the model of recognizing the pattern. Any model will always have some kind of limitation. If you are able to identify the limitations of your model, you might be able to use it in a better way. So there is a limitation of this simple model. Of course, this is a very simple perceptron, I know. So let's think of this simple task. We want to have our perceptron to work as a classifier again, but this classifier should fire when we have either 6 or 9, and 6 or 9 only. So it should not fire with, for example, 8 or 1. I will give you a hint here that it is not possible by using a single perceptron. In fact, this is not something new, and I will show you why. Now consider when I want this perceptron to fire. So I want it to fire in those situations. So here I have in every row an example of the input image and the corresponding features and the output that from the model. So if I have an input of digit number 1, I don't have the holes or the circles either in the top and the bottom. So this x is equivalent to 0. So you have 0, 0, and the output is 0. You have only 1 in the cases where you have exactly one of the two features is 1. And this is like an XOR function. And it's well documented that the perceptron, a single perceptron, cannot model an XOR function. In fact, the perceptron is a binary classifier. In fact, the perceptron is a linear classifier, as you may have observed from the way we constructed it. And it's a known fact that there is a linear model is not able to model XOR function. So I put some references here. The first is from Wikipedia, the other is from a very popular deep learning book. Before showing you the solution, you might want to take a moment to think about the possible way to construct a model for doing this classification task. I'm interested in only 6 or 9. And I already gave you a hint that you need multiple perceptrons. So take a moment to think about it, and we will be back soon. So hopefully you took some time to think about this. So here is a solution for it. So we have multiple perceptrons connected in a network like this. That's why we call it a network of perceptron. And the threshold that we have for each single perceptron, I put it inside the circle. And the weights are denoted over the arrows. So over each arrow, you would have the value of the weight associated to it. Now, this part is for the features coming from the top part of the image, and this is from the feature coming from the bottom part. So let's test it. So for 6, for example, you would have the feature only present in this one. What happens after that is that this perceptron will fire because you multiply 1 by 1, and this assumes that anything greater than or equal to 1, it will fire. This is 0, but it has no impact because we are summing here, so we still have the value of 1. Okay, and also this one will fire because, again, we will have the threshold of -1, and this threshold will be activated again by this. Okay. And since those two are firing and the threshold of this is 2, you would have the sum greater than or equal to 2. Again, you would have the classifier working. Now, if we try it with 9, you would have something like this. Feel free to work this example yourself. But for 8, we don't have the same case. Why? Because this one will not fire because the presence of the feature in the two cases mean that these two will be summed, it will be -2, and it's less than -1. So this one won't be fired. And a requirement for this to fire is to have those two activated. So again, this will produce a 0 at the end. So the goal of this classifier, it's this binary classifier, is to produce a 1 when the input is one of the classes I'm interested in and 0 otherwise. And this is what will happen in 8. Also, if you have 1, you would have the firing pattern like the example I'm showing here, and also it will give us 0. So the important question here is why it's not possible to model the problem of identifying either 6 or 9 using a single perceptron. So what I have here is a way to visualize the two features. So in the x-axis we have the features coming from the top part. So here it means that this feature is 1, and here it means that feature is 0. But also we have another axis for the bottom part. So it has the same notation, so it's 1 or 0. So here again it's 0, and here it's 1. And you have the combination of 1 and 0 here, here 0, 0, here 0 and 1. 0, 0 means that those features are absent. So you don't have circle either in the top or the bottom. Now, I mentioned before that the perceptron is a linear classifier. And the way it classifies things is that you just draw a line, and you have this line as your threshold. On one side, you would have all those classes you are interested in, and on the other side, you have the rest of the classes. For example, here, like 9, we know that 9, in the top part, we have 1, and in the bottom part, we have 0. And you can construct the classifier in this way. So this is the threshold, and anything beneath this threshold should produce a 1 or should be admissible as a class that the model should recognize. Other than that, it should be in this area. Okay. Now, say we are interested in 8. So 8 comes here. So it's 1 and 1. Again, I will construct the model this way. But what will happen if we are interested in 6 and the 9? Well, there is no easy way to draw a line that separates it from the rest of the classes. Because even if you have a line here, for example, you will consider 8. If you have here, you consider 8 and 1. So a single line wouldn't be sufficient for this problem. So it's logical to think of having two lines. So you would have a perceptron for this and another for this, and you combine them together. That's why we have 3 perceptrons in the previous, in the example I have shown. In this way, we can extend the capabilities of the single perceptron by constructing a network of multiple perceptrons. I guess this is the takeaway of this part. Now let's get to the question of learning the model weights and the threshold, the parameters of the model. Before answering this question, we will point one issue with the current perceptron configuration. So again, we will have set of inputs, and some computation is applied on those inputs. And we test against a specific threshold, and then we will have our output. Our output can be in one of two states, might be 1 or 0, okay? The key issue here is that we will have the output to switch in a way that's like a step function. So by this, let's give an example. This is a function that's not smooth because of the way that it's constructed, and it will cause an issue with learning. Why? Because imagine this scenario, you are searching for the model parameters that you don't know. So you construct a model and you have those weights. You will try to find a way to get those weights so that you could have the model that gives you the correct prediction, because you don't know them. One way to get those weights that you are after is that you start with some random weights and you continue to perturb them or change them until you have the optimal values. Okay, so you are searching for the best parameters for your model, or at least the parameters that gives you the expected results. And with this, we want to have this condition that if we make a small change in those values, since we are searching for something that we don't know, if we are making small changes in the weights, we have to have a corresponding small change in the output. let's give a visual example of this. So here again we have our perceptron, and we apply the computation and the thresholding, and we have the output at the location indicated by this red circle. So we make a small change in the first in the weights corresponding to the first input, and we have the output changing by this degree. If we do the same thing to input number 3, we again have this. But at one point, we might be doing something like this, a small change in input 2, or the weight corresponding to input 2, and we have the output changing dramatically. And what happens that we moved from this situation on the left to this situation on the right, as we did a very little change. The solution to this is having a smooth alternative. So rather than having this step function, we could have a function that's non-linear and smooth, like the one I'm showing here. Since we don't have the situation where we have the output constrained to be in one of two states only, rather we have this connected line between the red and black points, we can move gradually as we change the weights in the input to the perceptron. Compare this with the previous situation just to get a visual feel of how of what is the difference between the current situation and the previous one. So if you continue to do small changes, you gradually getting closer and closer to your target value. So what is the story so far? You could have two takeaways. One of them, when we had the situation of the limited modeling capability of a single perceptron, we had a network of perceptron instead of a single one, and we were able to model the XOR function. So you could have a network of perceptrons rather than one. And the other thing is that the smooth activations can make learning easier. Now, these two conditions are pretty much common in modern neural network architectures. Now, let's get to the neural network. In the standard terminology of neural network, we have the first layer is called the input layer. After the input layer, we have one or many hidden layers, and we finally have the output layer. Let's take a formal look into the single neuron. Now, the single neuron, usually denoted in the literature by a circle. Here, I put it as a triangle. And we have the following components. We have the input, we have the weights, we have activation function, and we have the output. Now the computation is done as the following. We apply the weights to the input and we do the summation as I mentioned previously. And after that we apply the activation. So let's put some symbols here. We will denote the input by X and weights by W, sigma for the activation and the A for the activation. Now the activation function here is sigma. The output is sometimes also called activation. Okay, so formally what happens that you apply the weights to the corresponding inputs and you do the summation. So you will have the sum of Xi, Wi. And you apply the nonlinearity or the activation function, sigma. And then you have your activation. Except that we missed one thing here, that we also have a bias. This p-value, it doesn't correspond to any input. It's associated with the perceptron itself, and also one of the learnable parameter. Once you add this into the equation, you could have this final form. But again, for simplification purposes, we will go back to the circle. But once you look into the circle, you should remember that this is what is happening. Okay.